So can you hear me? Yeah. We are running 30 minutes late, but that's fine. Today the afternoon is free, and for lunch we can also come a bit later. Don't think it's a problem there. For this afternoon in the program, so we have after lunch we have demonstrations on the T12 sample screening. Who hasn't seen that yesterday? Then we have another demonstration on the cryos. If somebody wants to go to the Titan cryos, and Hans Hebert will show us CCB4 in action in the computer room. Will we do this one after the other or on the same time? So what should we do? What is the plan for the computer room? Let's start with that. Okay, which is the time we have, so we should start that at 1:30 or whenever at 2 o'clock or whenever we are there. Radoslav, yeah? Yeah. Okay, so then the CCB4 demo will start, if you are half an hour late, probably at 2 o'clock or so. And who does not want to see that, but rather wants to go again to the Titan or to the T12 or something, can just do that, and we have the people and the experts there. And then at 3:30 or so, we will reconvene here for the final discussion and closing remarks. And we need to do this. I would please ask you to all come then. And after that, the program says free time, and I made the stupid idea to propose to go swimming in the Rhine. That's a bad idea. We have a high current at the moment. There was a lot of rain. The river is too fast. It's dangerous. Do not go into the water. Yeah? Death or serious injury may occur. So we take that off there. I'll be here in the computer room and would be available to show you more on 2DX image processing if anybody wants, but I can also understand if nobody shows up because we had 4 days of intensive program from early morning to late evening, so maybe we are all saturated. And the city is beautiful, the day is sunshine. So, and then at 7 p.m. we meet in this restaurant downtown, Löwenzahn. And if you go there by foot, you have no way then to see how beautiful the city is. It's a historic, nice city. So no swimming, optional to the image in the afternoon, and so on. So that's the program for the time being. Now I want to show you the projective constraint optimization thing. This is the story of Brian Gibson, who came as a programmer in 2005 to our lab in UC Davis. And after 2 years, where he implemented the Qt-based C++ part of the 2DX software, which is 2DX, we all agreed that he needs a PhD and will have a steep career. And so he started doing a PhD, and in 3 years he did that, starting in Davis and now finishing here. In the meantime, he got married and so on. And in the end, the last 6 months, he developed this, and I want to show you this. This is our way to address all the bottlenecks in elegant crystallography, and Andreas Engel is doing that at the same time. And we discussed this during the week. This is the last post-processing or refinement of your final structure, where we try to fill the missing cone, and address that problem. This idea is not new, even though when we started it, we didn't know that, but we found this out later. So it starts with the hybrid input-output algorithm of CNAP and Gershbeck-Saxton, and was tried in 1979 by David Elgart and Bob Stroud, and also Rainer Hegel worked on that later. They had very surprising results. For example, here a paper in 1982 linking regions between the helices and bacterial rhodopsin revealed the surface loops, which means they made some progress on the missing cone data. But then it faded into being forgotten or so, until John Spence took it up again together with Bob Glaser and Ken Downing, but they didn't reference this work neither, so maybe they also overlooked it. And actually they did. I spoke with John Spence at least. He didn't know about this. Who tried it on simulated data, pure computer simulation. So you take a PDB model, make some theoretical images out of that, and try to get the missing cone back, and that managed in theory. But this algorithm that I'm going to present is ultra sensitive to noise, exponentially sensitive to noise. So if you have real data, then you get into trouble. And so Brian nevertheless tried it, and I'll show you the results. So some background. We spoke about Fourier transformations a lot, yeah, that we have a real space shape like a rectangle, and you have a Fourier transformation of that, which in this case would be a sinc function, sinus x over x. And this applies also to our data when you have a structure and you have its Fourier transformation, then if that is noisy, then that is noisy. But if you multiply this with a rectangle, then you convolute your Fourier space with a sinc function. Yeah, so and that's why we can do the lattice line fit with sinc functions, because I'll come to this in the next slide. And when you convolute this with a different function, which is different than a rectangle, for example, something very complicated, you convolute your Fourier space with the Fourier transformation of this very complicated thing. And the more complicated this thing is, this mask, more than a rectangle, the more details does your convolution function have, your G, and therefore you have further outreaching convolution in Fourier space. We are dealing with proteins, and the Fourier transformation of a protein would be a density in Fourier space. And then we make this into a crystal, and that means we reduce our Fourier space to these lattice lines. It's the only thing that remains. And this crystal now in Fourier space has these lattice lines, and these lattice lines are the pixels in Fourier space from one lattice line to the next one. They have no neighborhood correlation. So one lattice line is completely independent of the values on the neighboring lattice line. But along one lattice line, we have Fourier pixel neighborhood correlation. So if you know this pixel along the lattice line, then probably you can predict the next one, the direct neighbor. Yeah, so there is Fourier pixel neighborhood correlation in the vertical direction only for 2D crystals. A single particle is different. And then we have this thing that we take our pictures, and the Fourier transformation goes as the central section in there. And we do this at different tilt angles, and we measure values along all these lattice lines. But we never reach the missing cone, because we can't tilt to higher than 60 degrees or maybe 70 or so. But we can't tilt to 90 degrees. So we have the missing cone problem. And so Brian started as a programmer, physics and mathematics and a little bit of biology, but he didn't know what a ton ring is, and he knew a bit about Fourier transformation and explained this to him and said, how do we go from here to there? Well, the Fourier transformation, FFT, and so. And then he had one of these 7 o'clock in the morning shower ideas, took a shower in the hot water on the head, and he said the Fourier transformation is linear. How linear is it? Well, very linear. So he used linear algebra to do that. He said, I don't use FFT to go from here to there with integral over exponential functions of imaginary stuff and so on. He uses a matrix. And so he said, I invent a new space, which is a reciprocal Fourier space in the horizontal H and K direction, but each lattice line I transform into real space. So this space is real in the vertical dimension and reciprocal in X and Y. And so each thing here, each thingy, is a real space transformation of one lattice line. So he invented this space. Nobody forbids this. Yeah? And so then he said, okay, how do I go from this real space lattice line to this Fourier space lattice line? Well, I need a function to go there, and this is now supposed to be a linear function. So, and then he came up with a matrix, and he says, well, I take linear algebra, a matrix, it goes from this lattice line to that lattice line, yeah, or this one to that one. For each lattice line, a matrix. And the matrices that are involved are large. So here you have one real space lattice line, and here you have the Fourier space lattice line, and you go there with this matrix F. And he came up with a way how to calculate that. And the matrix F has as many rows as you have pixels in your real space lattice line. There you have one pixel is 1 angstrom, and you have a 5 nanometer membrane, so that's 50 pixels. So there's 50 pixels here. And then you have your measurements from your pictures. Let's say you have 200 pictures, and you have a P4 symmetry that gives you 800 measurements on one lattice line. And so you have 800 measurements, but they are not equally spaced. They are on some funny positions, depending on the tilt angles. Yes, you have many non-tilted pictures, and then some 30-degree, and so you have an uneven spacing. And so you have a matrix F now that has 50 times 800 elements, and translates this thing into the positions on this lattice line, but non-equally spaced, which is the important part. And then you can transform your real space lattice line into your measurements without the need to interpolate, because you're non-equally spaced here along this lattice line in reciprocal space, and you want to go back. Now you have to invert this very large matrix, and you can do this with linear algebra with a method called singular value decomposition, where you take your matrix and you diagonalize it by having some coordinate transformations before and afterwards, and you invert these by just transposing them, and to invert a diagonalized matrix is easy with a least square algorithm, approximately at least. And you have your inverted matrix with which you can go back. So that's linear algebra, that's standard in mathematics. So you have now a matrix to go here and back. And the important thing is this is equally spaced. Every 1 angstrom is 1 element. And this here is non-equally spaced, which is your measurements. So we go here and back. And you implement this on a GPU, so it's super fast. Yeah, we use Tesla cards. And then we have to go from here to real space. So then this is equally spaced. Then you go a normal FFT forward, then you are back in lattice lines, but now it's equally spaced lattice lines, and then you have a 3-dimensional volume so this is experimentally unevenly spaced, and this is evenly spaced, and here is a 3D FFT, then you are here. And now you have a way to go from here to there and back without the need to interpolate some bins along your lattice lines. You go directly to the measurement positions there. And you can do this very, very fast using GPU hardware. And then you can now oscillate very fast between real space and your measurement Fourier space. And we apply boundary conditions. So we oscillate between this and that back and forth, and we apply boundary conditions in real space. We say our volume is real. We don't have negative densities. We may have a symmetry, P4 or something, and we have a membrane slab. There's nothing above and nothing below our crystals. There's just water or maybe a carbon film, but there shouldn't be anything visible above and below your membrane protein crystal. And then in your measurements, you know your amplitudes and your phases, and you can say, well, I know those are true. Those are other knowns that we can enforce. And then if you then oscillate between here and there, you can also enforce other constraints, like the resolution range. I don't want to see any data show up at 0.001 angstrom resolution. There's only noise. My microscope doesn't go there. We know a scattering profile, an approximate one. You can look it up in the PDB, or you take some SAX data or so. And so you oscillate back and forth hundreds of times, each time applying these boundary conditions. But you use individual weights for all these constraints. So if you know an amplitude precisely with a very good figure of merit, then you really enforce it. And if you have some estimate about some amplitude with a bad figure of merit, you're careful with enforcing that. And you apply your constraints only in fractions, only 5% of what you want to apply. That means if you want to delete density above and below your volume because you say there shouldn't be there, you don't delete it, you only weaken it by a few percent in each iteration. And then after doing this, you come up with some better idea about your protein, and you can use this to apply a shrink wrap algorithm to have a better mask here. Because the first slab foundation mask is a rectangle, corresponds to sinc function convolution. But now if you come up with a shrink wrap around your approximate density of your protein, you come up with a very complicated mask that you can apply here. And that is equivalent to convoluting your Fourier space with a very long, high-resolution function that is different than sinc. And therefore, you can have more neighborhood correlation along a lattice line than originally. And in addition, you can do some edge detection here and noise suppression. So you just do all kinds of thresholding and skeletonization, and so to really come up with a very nice thin mask around your carbon backbone without knowing anything about your structure. You don't know that it's a protein. It could be whatever. So, and then he applies this and goes forward and backward with applying all these boundary conditions and iterates back and forth. There are different ways to apply this. You come to a solution, there are different ways to apply this. And then you get to a converging method. And the question is then, is that a good one or not? And so Bryant added a swarm optimization algorithm that when you found one solution in the end, which is the old position, you perturb that with a random offset. So you add some noisy stuff to your 3D reconstruction in the end, and then let that try as a new position, but still add another little bit of a vector for your last locally known best position, plus a step into the direction of the best globally known position, the best globally known 3D reconstruction. And you do this with 100 different swarm Bs that swarm out. And this is a swarm algorithm that can be used to find a global best solution without the risk to be trapped in a local minimum. Yeah, swarm optimizers are used in many fields. So you try 100 times with different perturbances, and you have a personal memory, and you have a global communication between particles, and you have parameters A, B, and C that determine how fast you go there, or how big the risk is that you get stuck in a local minimum. So you come up with a refined 3D reconstruction, and then your critics ask you, is that true or not? So you need a measure. And we came up with this cylindrical ring correlation. So this is a space where you have X and Y horizontally and Z vertically in Fourier space. So, and this is the known data here, where you see the missing cone here. And now this is the intensity, and this is the Fourier ring correlation, where we place a ring in our 3D volume. So this is your 3D volume in Fourier space, X and Y and Z in Fourier space. You calculate the ring correlation along this ring of a certain radius and a certain height for all the pixels along this ring, and check, for example, if you find your P4 symmetry for the pixels along this ring, or your P3 symmetry. We started with bacteriorhodopsine. So there should be a P3 symmetry for the pixels along this ring. And we check if we find a P3 symmetry for this ring, and if we do so, it becomes a bright value, blue, and if not, it's a red value. And so you can check for P3 symmetry in Fourier space. And you see for the original data, there's intensity and there's P3 correlation for the data outside of the missing cone, but otherwise there's the missing cone. So this is our measure to see if we do it right or not. When you apply this to test data like this volume, and you have a full Fourier representation in X and Y and in Z of this, and then you cut out the missing cone, then you have an artifact in your test volume. And others have done this before. This is the missing cone, how it looks in your 3D reconstruction, and this is the missing cone, how it looks in Fourier space. And when you apply this algorithm, and you start with either zeros in the Fourier space, or you start with noise in the Fourier space as a starting model, and then let the algorithm run, you grow back your missing cone. And we wanted to see what is the best starting model, zeros or noise, and it turns out that zeros are the best starting model, because this grows out faster into the missing cone than if you start with noise, where you create some funny horizontal lines of known and unknown regions or perturbances that are very slow to get away with. So the much better starting position is to really accept that there is unknowns, and you put them to zero and don't put noise in there. And then you can reconstruct the missing cone, and you can have this disappear, but this is noise-free. And John Spence showed that this works. So in the absence of noise, it works nicely. And now we went and looked for a very good data set, which Kaoru Mitsuoka had from the data from Yoshinori Fujiyoshi. And they published in 1997 this Komura et al. Paper on bacteriorhodopsine, and this is a figure from the data set where they had a missing cone problem, obviously. So you have the, I think, so this is close to the shift base. You have the helices, and sometimes you have densities that shouldn't be there, and some of the residues were not visible. They thought maybe they are charged, but in any case, they didn't see them. And we also have an X-ray structure now from Essen et al., determined later, and that was determined in the presence of lipids, but with X-rays. At 2.8 angstrom resolution, this was 3.0 angstrom resolution from electron microscopy. So we got these data, and we got the raw data, amplitudes and phases, electron diffraction and images without any processing. And Bryant applied this algorithm. This is the first 3D reconstruction he made out of that, and then applied this processing with initially 100 rounds oscillating between real space and Fourier space. And then in the last 30 additional rounds, added the shrink wrap to it. And then if you look at this location in the middle of the protein through these rounds, it slowly converges to some solution. This is the final iteration after the particle optimization. And we believed it looks better. If you look at different locations in this protein, so here's what they had in the publication, close to the shift base. There's this density that shouldn't be there. This is invisible, and this algorithm then tries to fill in data in the missing cone and corrects things, and especially the shrink wrap in the end is a very fast way to converge to something. But you need first slight refinement to put the shrink wrap algorithm to the correct densities. And then now these side chains show up, and the forbidden things that shouldn't be there, they get weaker. We also found lipids in this refined structure which were not noticed and described before. This is in the center of the fourfold, of the threefold trimeric thing. These lipids were not visible before the refinement. So this is the full data set with the X-ray model in there, and this is the center of this trimer, where we have these lipid densities. The atomic model that you see here is the model from the X-ray structure, which also had lipids, whereas the density comes only from the electron microscopy data after missing cone reconstruction. These lipids were in the center, and there's also lipids on the outside now, which we can see. This is the X-ray model and the electron microscopy density, and the electron microscopy density here in some cases goes clearly into different directions. And those were different lipids. Yeah, so one is from the BR purple membrane reconstituted, and the other one was from the X-ray work by Essen et al. Especially this horizontal branch here, which we interpret as a lipid polycarbon tail, was completely invisible before that. So this is the figure that Bryant made comparing his refined data with the original data before the refinement. The surface loops are better visible at only one isocontouring level, and you have some side chains that are now better resolved than before. I don't find this so telling, this figure. So then we have our measure. This is before the refinement, and this is after the refinement. And here we have the intensity, and here we have the Fourier ring correlation. And the Fourier ring correlation shows us that in the missing cone we have intensity and also significant intensity here. This is a very high resolution. The algorithm works equally well at lower resolution. This is a water channel data set that shows alpha helices, looks like 7 angstrom resolution or so, smooth helices in the beginning, no loops, no side chains. And when you run this algorithm on it, you see a little bit of corkscrew and more horizontal connections than before. Here's another set, it's pretty dark here. This is before the refinement, one alpha helix here, another one here. This shouldn't really be there. And this is after refinement, where you have a little bit of corkscrew, and this fits to the periodicity that you would predict. The corkscrew, carbon backbone, and maybe some side chains, but maybe not. So the implementation that Bryant has done is running in MATLAB and uses Tesla cards. And this oscillation does this matrix calculation and needs the Tesla GPU. For that, you do it once and come to one first model, then you perturb that into 100 copies and try all of them with a swarm optimization. They have a local minimum and a global one, and you try to have them, the swarm, converge to one optimal solution. And optimal is the one where you have the lowest amount of corrections during your enforcing of boundary conditions necessary. And then you use that final chosen best optimum as your solution, and that is what we call projective constraint optimization. And you can do this after all your 3D reconstruction. So you can have your 3D reconstruction, you can do a post-processing with a future version of the maximum likelihood 3D single particle thing that Xiang Yang is working on. And when you have your final data set in Fourier space, you can run this projective constraint optimization to try to further improve data in the vertical direction especially. and then have your result. And this is the PhD of Brian Gibson. Involved there is also, so Xiang Yang was involved in this in the beginning, and Marcel and Daniel are now also in the software team, and Raphael will join 1st of December. He was here until yesterday. And that is the project of constraint optimization that I wanted to show you. Yeah, Richard?
You know what the R values and the phase residuals were for the amplitude and phases that you found within the missing cone?
I don't know them by heart, but we have calculated those, and there were surprising numbers. Yeah, for phase residuals and R values, I just can't spit it out right now. I would have to look it up. So they compared. The thing gets better, and we have significant correct densities in the missing cone. But there was one issue of contradiction, which we interpreted as that the I just can't spit it out right now. So sorry. I would have to prepare that answer a bit better. Hansi?
You said the lipid density that you found after the optimization wasn't there before. From what I understand of the mystical impact, you can't produce things without something already there.
So the density that shows up in the lipids, the information about that was included in the data set, but distributed over the entire data set. And we put additional knowledge into the system by saying we have a carbon backbone. That is an additional knowledge, which is not included in the data set. Yeah? So this whole approach does not only use the data that you have in your data set and try to make some sense out of that. This is this slide here. So you have measurement data, which is your one data set, and then you add additional data, which the most important one or most effective one is a shrink wrap, where you say, in addition to my measurement data, I know that this is a protein that is a snake. Yeah, and this is comparable to the work that a model builder would do in the latest refinement stages, where you have your density and you build some model, including loops, a PDB model, and then Fourier transform that and take the phases from that to further refine your model in the end. You can do this effectively manually, but here it runs automatically. And if you do this, you would lose individual water molecules, but you can try to grow them back later. So the lipids that we see in the end, traces of that must have been there before, but with a very elongated point splash function, so that they were below the threshold, the contouring threshold, to make them visible. Yeah, we can't grow it from nothing, but there must have been the data somewhere in the data set. Yeah. Hans, yeah? No, we don't use any model. So the first shrink wrap skin is just taken from the reconstruction that you at that point have, just putting some isocontouring threshold there, and then you can shrink that and grow it out again so that you get rid of outliers of individual blobs that are not connected to your volume. And you end up with some skeletonized skin, yeah? So you use that as a mask, and you can then sharpen the mask with this edge detection algorithm. And inside of that mask, still go for noise pixels and try to either fill them in or dilute them. It's just what you would do in computer graphics in a two-dimensional picture if you want to smooth things. So I think it's skeletonization and extension of mask. Photoshop has these in 2D. And Brian applied this in 3D to this initial volume. It comes only from the data set itself. So it would also work with some funny polymer that is not a protein. Yeah? it's a good idea. So you have in Fourier space your measurement data, and in the missing cone you take at least the amplitudes of the average membrane protein structure from the PDB and put those there, and then hope that the phases come out from the rest. That's a good idea, and it's similar to enforcing the scattering profile here. So we found, or Brian found, that it converts fastest into the missing cone by diluting this energy out into the missing cone, but you can rescale it up. If you start with zeros, then you don't have any obstacles from wrong known numbers. And during this, you can still apply a scattering profile, which is similar to what you say, a radial scattering profile. So you look in that direction, you should on average expect the following envelope function for your intensities. And you apply that carefully, not overdoing it, only fractionally. That's similar to what you propose. So he just found that the convergence is fastest if you start with zeros. So this will become available in 2DX in a few months, we hope. At the moment, it runs in MATLAB with all the computationally intensive stuff here for these matrices on a Tesla card. And if you know what to run it on Linux or Macintosh on your portable computer, and you don't want to have to wait a month for this step, we have to reprogram things. You don't have the Tesla card cluster there. So Brian started working on this, but then spent his honeymoon vacations there, and now he's in Houston, Texas, in the lab of Lydia Kravaraki, and he wants to still work on this, he said, and put this into 2DX. So I think in a few months you should all be able to test this out, and it will be distributed with source code. We just have to find a solution for this GPU requirement, speed-wise. Bob Glaser was very critical when I told this on the Gordon conference a few weeks ago, and then he said, well, you should do this and that, and then I said, okay, so how about I will give you the full data set before and after refinement, and you figure out yourself if it's better or not. That would be one way to address the criticisms. Yeah, we just put the raw data and the refined data public, plus the algorithm. Everybody can repeat it, and then everybody can see what, if they also agree that we believe that the data that are generated in the missing cone are significant and true, and actually the resolution in Z at the end is higher than in X and Y. Yeah, so it's not only missing and not missing anymore, it's the best resolution in the end is in Z, which also is okay theoretically. Yeah, from the very tight oversampling at low resolution and low tilt angles, you can perfectly predict what you have at very high one-angstrom resolution in the vertical direction, which I think is shocking. So, okay. That's what I wanted to say.